We choose to go to the moon in this decade and do the other things. Not because they are easy, but because they are hard.
Godspeed, John Glenn.
Roger, 0G, and I feel fine.
Get my feet up. Okay, I'm out.
How does it feel for the United States to be the new record holder?
At last, huh? When that baby lights, there's no doubt about it.
Liftoff. We have a liftoff. 32 minutes past the hour. Liftoff on Apollo 11.
Houston, Tranquility Base here. The Eagle has landed.
That's one small step for man, one giant leap for mankind.
Hello and welcome. This is Michael Annis, and you're listening to episode 126 of the Space Rocket History Podcast. And now, Saturn IB, AS-201, AS-202, and AS-203. After the Saturn I flights and the last Little Joe flight, the scene shifted to Florida, where a Saturn IB test program was about to begin. We will start with the first flight of Apollo-Saturn 201, AS-201. AS-201 employed the Saturn IB, which was the uprated version of the Saturn I rocket flown in 10 earlier Apollo missions. It featured an upgrade of the first stage engines to increase thrust from 1,500,000 pound-feet of thrust to 1.6 million pound-feet of thrust. The second stage was the S-IVB. You may recall this stage used a liquid hydrogen-burning J2 engine, which would also be used on the S2 stage of the Saturn V lunar launch vehicle. AS-201 also used a new model of the guidance and control system known as the instrument unit, which would also be used on the Saturn V. Saturn IB first stage, with its 8 H-1 engines built by Rocketdyne, was assembled by Chrysler and delivered to the Cape via the barge called Promise. It was erected on Launch Complex 34 at Cape Kennedy in August 1965. The new S-4B stage, built by Douglas, arrived next on September 18th. On August 1st, it was mated to the first stage and check-out began. The 1,800 kilogram instrument unit that controlled the launch vehicle, made by IBM Federal Systems Division, arrived on October 22nd. After repairing some problems, it was mated to the S-4B stage on October 25th. The Command and Service Module, CSM-009, was a Block 1 version designed before Lunar Orbit Rendezvous was chosen as the method to go to the Moon. Therefore, it lacked capability to dock with the Apollo lunar module. Block 1 also employed preliminary designs of certain subsystems and was heavier than the Block 2 version with lunar missions capability. All previous command and service modules flown, with one exception, were boilerplate versions. Command Module 009 assembly began in October 1963 and continued throughout 1964, with the inner shell aluminum honeycomb pressure vessel taking shape concurrently with the stainless steel honeycomb outer shell and its ablative heat shield. By April 1965, 009 had reached the test division at Downey, where it spent the summer. After a review at the factory on October 20th, NASA Apollo engineers approved the spacecraft for shipment to Cape Kennedy. Command Module 009 was the second production Block 1 command module to fly, the first being Command Module 002, flown on a Little Joe 2 rocket for the final Launch Escape System Abort Test, designated A004. Command Module 009 varied from the production configuration by the omission of the guidance and navigation system, crew couches, displays, and associated equipment, and by the addition of a control programmer and open-loop emergency detection system. Service Module 009 was the first production Block 1 service module to fly. It varied from the production configuration by replacement of the electrical power generating fuel cells with batteries and omission of the S-band communication equipment. The command module arrived at the Cape on October 23rd and the service module on October 27th. Command and Service Module 009 was hoisted atop the booster on December 26th. The top third of the stack, the spacecraft, lunar vehicle adapter, the cylindrical service module, the conical command module, and the pylon-shaped launch escape tower was all North Americans' responsibility. Once they were stacked together, NASA assumed control. During the checkout procedure of the AS-201, several problems occurred. The first problem encountered by NASA came on October 7th. The RCA-110A computer, which would test the rocket and thus automating the process, was 10 days behind schedule, which meant that it would not be at the Cape before November 1st. This meant that by the middle of October, little could be done at the pad. When the computer finally did arrive, it continued to have problems with the punch cards. And when the clock rolled over from 2400 to 0001, it also failed. Testing was running around the clock during December. Technicians were testing the command service module's fuel systems during the day and the rocket at night. Okay, let's move on to mission objectives. It actually took 2 pages to list AS-201's test objectives, but here is a bullet point summary. The objectives were to demonstrate the Saturn IB launch vehicle propulsion, guidance, and electrical systems. Demonstrate structural compatibility between the launch vehicle and the command service module, ensuring the spacecraft's design loads weren't exceeded. Demonstrate appropriate separation of all vehicle elements. Demonstrate the command service module's heat shield, service propulsion system, including in-space restart, command module and service module reaction control system, environmental control of the cabin pressure and temperature, partial communications, stability and control, Earth landing system, and electrical power subsystem. Evaluate the emergency detection system in an open-loop configuration. Demonstrate the command module heat shield ablator at a 200 BTUs foot squared per second heat transfer rate. Demonstrate support facilities for launch, mission control, and recovery. To sum it up, the primary objectives of this mission were to demonstrate the integrity of the launch vehicle, compatibility of the spacecraft, and verification of the operation of the spacecraft, entry heat shield, and recovery system. The mission called for the Saturn IB to launch the spacecraft on an east by southeast heading into a high ballistic trajectory. Then the command service module would separate. The service module engine would be fired twice. Then the command module would re-enter and land in the South Atlantic Ocean. Here's an audio clip.
Apollo goals came closer to operational status with the arrival of the first production Apollo spacecraft at the Kennedy Space Center in October 1965. Following an extensive program of inspections, cleaning, build-up, and testing, the mated command and service modules provided the first view of flight-configured Apollo spacecraft modules. On December 26th, the command and service modules and the attached adapter section were mated to the Saturn IB launch vehicle 201 at Launch Complex 34. Saturn launch vehicle development is under the direction of the Marshall Space Flight Center, Huntsville, Alabama. Throughout January and February of 1966, pre-flight tests were conducted to ensure every possibility of mission success. The unmanned spacecraft was scheduled to be launched on a 5,000-mile ballistic trajectory down the Atlantic Test Range. The mission would also help confirm the all-up concept of flight testing, in which all launch vehicle and spacecraft components will be flown together live for the first time.
On February 20th, 1966, launch technicians at the Cape began a 3-day countdown, fully expecting some of the spacecraft systems to delay the launch. But weather turned out to be the chief problem, causing 2 postponements. At 5:15 on the afternoon of February 25th, the countdown resumed. 3 seconds before ignition at 9 o'clock the next morning, a computer signal that pressure in 2 helium spheres on the Saturn IB was below the danger line. The count was recycled to 15 minutes before launch and stopped. Discussions waxed hot between Huntsville and Cape engineers, since no one could be sure just how serious the problem really was. The mission was scrubbed at 10:45 a.m. Later, deciding that the drop in pressure was probably caused by either an excessive flow of oxygen in the checkout equipment or leakage in the flight system, Furneaux and Brown's Saturn team recommended advancing the ground pressure regulator to maintain a higher pressure in the spheres. Kurt Debusse's team agreed. After running a simulated launch and 150 seconds of flight to show that the rocket could operate with the lower pressure in the fuel tank, the launch was reinstated and back on track by 10:57 a.m. At 11:12 a.m., February 26th, AS-201's first stage ignited and drove the combined vehicles up to 57 kilometers, where, after separation, the S-4B took over, propelling the payload up to 425 kilometers. The second stage then dropped off, and the spacecraft coasted in an arc, reaching a peak altitude of 488 kilometers. At the zenith, the service module engine fired for 184 seconds, hurtling the command module into a steep descent. After a 10-second cutoff, the rocket engine fired again for 10 seconds to prove it could restart, which was crucial for lunar missions. The 2 modules then separated, the command module, traveling at 8,300 meters per second, turned blunt end forward to meet the friction caused by the growing density of the atmosphere, but it rolled the wrong way and missed its intended target point in the Atlantic. However, both booster and spacecraft performed adequately. From liftoff in Florida to touchdown in the South Atlantic, the mission lasted only 37 minutes. Here's a clip.
On launch morning, February 26th, low gaseous control pressures in the launch vehicle forced several recyclings of the countdown and an eventual scrub. However, 10 minutes later, the problem was corrected and the scrub decision was reversed. At 11:12 a.m. Eastern Standard Time, February 26th, Apollo-Saturn mission 201 was on its way. Staging occurred approximately 2.5 minutes after launch. The 200,000-pound thrust second stage engine then ignited and propelled the spacecraft to a 310-mile altitude. 40 minutes later, the command module landed approximately 43 nautical miles short of its predicted impact point.
The capsule splashed down 72 kilometers from the planned point. Since the landing was off target, it took 2.5 hours after splashdown for the capsule to be recovered by the USS Boxer. In conclusion, AS-201 proved that the spacecraft was structurally sound, and most important, that the heat shield could survive an atmospheric re-entry. There were several malfunctions, mostly minor, but 3 were serious. First, after the service propulsion system fired, it operated correctly for only 80 seconds. Then the pressure fell below 30% because of helium ingestion into the oxidizer chamber. Second, a fault in the electrical power system caused a loss of steering control, resulting in a rolling re-entry. And third, flight measurements during re-entry were distorted because of a short circuit. Although Miller agreed that the mission objectives had been met, these 3 problems would have to be corrected. The service module engine received instant attention. North American's Robert E. Field and Aerojet General's Dan David ordered an analysis of what had gone wrong. The engine had operated well enough to finish the mission, but Field and David had to be sure that the Block 2 engine, currently undergoing ground testing, would not run into a similar situation during a lunar mission. They learned that a leak in an oxidizer line had permitted helium to mix with the oxidizer, causing the drop in temperature and pressure. For all of Houston's insistence on redundancy, this was one major system that had no backup, and it was a vital system. Because of the lunar orbit rendezvous decision, the service module engine had a variety of jobs, such as mid-course corrections on the way to the moon, lunar orbit insertion, and trans-Earth injection on the return voyage. Weight penalties prevented a second propulsion system. The service module engine had to carry its own built-in reliability. AS-201 did not get a lot of publicity, but Dale Myers and his North American crew considered its spacecraft 009 their teething operation. Myers is quoted as saying, quote, "It proved out our procedures, our checkout techniques, and proved that this equipment fit together. And we got lined up so we were able to handle operations both at the Cape and in Downey. Although spacecraft 009 had some problems in flight, we got what we were looking for from the primary objective, real good data on our heat shield, which we just can't get any testing on in any other way." End quote. On the whole, it was a successful mission, although system testing would be required to solve the persistent problems. Now here's an audio clip.
Recovery was performed by crews aboard the carrier Boxer. Mission objectives included subjecting the command module's heat shield to a fast re-entry heat buildup. 2 burns of the service propulsion subsystem accelerated the re-entry speed of the spacecraft so that heat rate buildup approached the values that will be encountered during lunar mission re-entries. Fluctuations in SPS engine firing chamber pressures degraded the entry velocity, resulting in lower surface temperatures than planned. However, data protractions verified that the current heat shield design is able to withstand an atmospheric entry from a lunar mission. The successful completion of the first Apollo-Saturn mission was one of the most important accomplishments to date in the development of a manned lunar mission capability. In summary, progress during the reporting period saw Apollo system hardware in manned qualification testing. There were problems, but they were overcome with no distress to overall schedules. Flight article Apollo spacecraft have started to come off the assembly line. And subsystems tests have given way to full-scale flight verification testing. In all levels of Apollo spacecraft activity, program milestones continued to point the way to a scheduled manned lunar landing within this decade.
Strangely enough, the next Saturn IB mission was AS-203. In order to allow time for studying and solving propulsion system problems and to prevent program delays, NASA managers shuffled the launch sequence. Since AS-203 was not scheduled to carry a payload, it was flown before AS-202. The S-4B stage for AS-203 arrived at Cape Canaveral on April 6, 1966. The S-1B first stage arrived 6 days later, and the instrument unit came 2 days after that. On April 19th, technicians began to erect the booster at Pad 37B. Once again, the testing regime ran into problems that had plagued AS-201, including cracked solder joints in the printed circuit boards, requiring over 8,000 to be replaced. Now, let's pause briefly to identify a unique event. In June 1966, a view presented itself at the Cape. 3 Saturn rockets could be seen set up on various pads across the Cape. At Pad 39A was a full-sized mock-up of the Saturn V. AS-202 was on Pad 34, and AS-203 was at 37B. Now, continuing with the objectives of AS-203. The purpose of the flight was to investigate the effects of weightlessness on the liquid hydrogen fuel in the S-4B second stage tank. The lunar missions would be using a modified version of the S-4B as the third stage of the Saturn V launch vehicle. This called for the stage to fire briefly to put the spacecraft into a parking Earth orbit before restarting the engine for the flight to the moon. In order to design this capability, engineers needed to verify that the anti-slosh measures designed to control the hydrogen's location in the tank were adequate, and that the fuel lines and the engines could be kept at the proper temperatures to allow engine restart. In order to keep residual propellants in the tank on orbit, there would be no Apollo command service module payloads, as there were on AS-201 and 202. The command service module was replaced by an aerodynamic nose cone. Also, the full load of liquid oxygen oxidizer was shorted slightly so that the amount of hydrogen remaining would approximate that of the Saturn V parking orbit. The tank was equipped with 88 sensors and 2 TV cameras to record the fuel's behavior. This was also the first flight of a new type of instrument unit that controlled the Saturn rockets during launch, and also the first launch of a Saturn IB from Pad 37B. Now on to the flight. On July 5, 1966, AS-203 launched on the first attempt. The 26,500 kilogram second stage S-4B and instrument unit were inserted into a 190-kilometer circular orbit. Ground observers monitored the S-4B by television, watching the 8,600 kilograms of liquid hydrogen remaining in its tanks. The television camera provided views of the successful demonstration of settling the hydrogen by the venting of gas into the tank, which pushed the remaining propellants toward the rear of the tank, where valves took the fuel into the engine system. The controllers were so amazed by the television pictures from inside the tank that they thought they were looking at earlier simulations. They had to confirm that the simulator was turned off and what they were watching was actually SA-203 hardware in orbit. The S-4B design test objectives were carried out on the first two orbits, and the hydrogen was found to behave mostly as predicted, with sufficient control over its location and of engine temperatures required for restart. The next two orbits were used for extra experiments to obtain information for use in future cryogenic stage designs. These included a free coast experiment to observe and control the negative acceleration of the fuel caused by small amounts of aerodynamic drag on the vehicle, a rapid fuel tank depressurization test, and a closed fuel tank pressurization test. The closed fuel tank experiment involved pressurizing the hydrogen tank by closing its vents, while depressurizing the oxygen tank by allowing it to continue venting. It was expected that the pressure difference between the two tanks would collapse the common bulkhead separating them, as confirmed in a ground test. The rupture must have occurred during the first 2-minute loss of signal between the Manned Spacecraft Center and the Trinidad tracking station. The Trinidad radar image indicated the vehicle was in multiple pieces, and telemetry was never reacquired. NASA concluded that a spark or impact must have ignited the propellants, causing an explosion. Despite some turbulence, the S-4B appeared capable of boosting the astronauts on a flight path to the moon. Despite the destruction of the stage, the mission was classified as a success, having achieved all of its primary objectives and validating the design concept of the restartable S-4B. In September, Douglas Aircraft Company, which built the S-4B, declared that the design was ready for use on the Saturn V to send men to the moon. Okay, let's move forward to the final mission I want to cover on this episode, AS-202. Mission AS-202 was twice as complicated as AS-201. It would last 90 minutes, reaching an altitude of 100 kilometers, and travel 2/3 of the way around the world. The AS-202 mission was designed to test the Saturn IB rocket more intensely than AS-201. This was accomplished by launching the rocket higher and having the flight last longer. The flight would also test the Command and Service Module 011 by having the engine fire 4 times during the flight. Of course, the mission was also designed to test the heat shield by subjecting it to 260 megajoules per square meter. Over the course of re-entry, it generated equivalent energy needed to power Los Angeles for over 1 minute in 1966. Command Service Module 011 was basically a production model capable of carrying crew. However, it lacked the crew couches and some displays that would be included on later missions for the astronauts. This was the first flight of the guidance and navigation system, as well as the fuel cell electrical system. On August 25th, 1966, AS-202 was successfully launched from Pad 34. The launch phase was nominal, with the first stage burning for just under 2.5 minutes, lifting the rocket to an altitude of 56 kilometers downrange from the launch pad. The second stage then burned for a further 7.5 minutes, putting the spacecraft into a ballistic trajectory. The Command and Service Module was separated from the rocket stage at an altitude of 777 kilometers. The Command Service Module was programmed to make 4 burns of its service propulsion system. The first occurred a couple of seconds after separation from the S-4B second stage. It burned for 3 minutes 35 seconds, lifting the spacecraft apogee to 1,143 kilometers. The second burn was 25 minutes later, lasting 1 minute 28 seconds. 10 seconds later, 2 more burns of 3 seconds each were done to test the rapid restart capabilities of the engine. The command module entered the atmosphere at a speed of 8,690 meters per second. The spacecraft performed a skip re-entry, first descending to 67 kilometers, then lifting back up to 81 kilometers. By this time, it shed 1,300 meters per second of speed. It then continued to descend. The main parachute deployed at 7,250 meters. It splashed down near Wake Island, 380 kilometers from the target landing site, and the USS Hornet took 8.5 hours to reach the capsule. On the carrier, specialists found that the heat shield and capsule had come through re-entry admirably. This, coupled with the 4 precision firings of the service module engine, made AS-202 a very successful flight. Thanks for listening to this archive episode of the Space Rocket History Podcast. If you are financially able, please support the podcast by going to the homepage, spacerockethistory.com, and clicking on the orange Donate button or the Patreon link. Thanks.